And this slide here is pretty much this chapter. This slide here will help you understand how to answer pretty much any given problem in thermodynamic in terms of understanding what the system is under. So we are considering an ideal gas. So this ideal gas is going to follow all the ideal gas laws, which mean Boyle's law, Charles' law, Avogadro's law, and ideal gas law, which is BV equal nRT. We're going to be always using the first law of thermodynamics that relate delta U to Q to W. And we're going to have 4 different variables. We're going to be working under 4 different experimental conditions. The first experimental condition is isothermal condition. If you are working under isothermal condition, what this mean? It means the change in temperature is equal 0. Your temperature is constant. When you say isothermal, that means your temperature is constant. That means your delta T is 0. And remember, I just mentioned to you the equation for delta U and delta H. Delta U is equal NCVM delta T, and delta H equal NCBM delta T. So both of these are related to the temperature change. And if the temperature change is 0, there is no internal energy, there is no enthalpy change. So both delta H and delta U will be 0. So this is a very important conclusion here. When you are working under isothermal condition, there will be no change in internal energy, neither there will be no change in the enthalpy because your delta T is 0. All right? So applying this law here, if delta U is 0, what will be the Q and the W related to each other? Q will equal negative W. So under isothermal condition, delta U will equal 0, delta H will equal 0, and Q will equal negative W. All right, so this is the first condition, which is isothermal condition. And the problem is going to be telling you that you're working under isothermal condition. So you will know exactly what condition you're working on. The second condition is isochore. Isochore condition mean your volume is constant. This gas is under constant volume, which mean a fixed volume. The volume doesn't change. No matter how much heat you apply, the volume doesn't change. It's a fixed container. So the volume is 0. Not the volume is 0, the change in volume is 0. If the change in volume is 0, then the work is 0, because remember the work is negative B delta V. So by just saying isochore condition, by just saying you're working at constant volume, you immediately said the work is 0. Doesn't matter what the gas is doing, the volume doesn't change. And that basically means the work is 0. So we know already what delta U and delta H equal. Again, they equal this, NCVM delta T and NCBM delta T. So this is a very important equation that you will determine delta U and delta H through this. So, and we know already that delta U here is equal Q. Why delta U equal Q? Because this is 0. If the work is 0, then delta U equal Q. And what is delta U equal to? NCVM delta T. So this is very, very important. So when the question asks you to determine delta U and determine Q and determine W and delta H at isochoric condition, you will say that W is going to equal 0 because this is a constant volume, which means delta V is 0. And delta U will equal Q because that's, again, according to the first law of thermodynamics, W is 0 here. And what is delta U equal to? Equal NCVM delta T. You will be provided with CVM, you provide with number of moles, and you provide with the temperature change. So you can calculate delta U and Q. And how can you calculate delta H? Again, NCBM delta T. You'll be provided with CVM. You will be able to determine CBM. I will show you how you can get CVM from CBM or CBM from CVM. There is a relationship that relates both of these. It will be revealed right now, in about a minute from now. All right, isobaric condition. This is the third experimental variable. Working under isobaric condition. What's isobaric condition mean? Constant pressure. Your pressure is constant. If your pressure doesn't change, then the change in pressure is equal 0. Delta B equals 0. That doesn't mean the pressure is 0. The change in pressure is 0. That doesn't mean the temperature is 0. The change in temperature is 0. That doesn't mean the volume is 0. The change in volume is 0. So that's a huge difference between a volume is 0 or a change in volume. So again, if delta B is equal 0, none of these is going to be 0 because really there's nothing here. Delta U will be still NCVM delta T. We'll be able to determine delta U. Delta H will equal Q because it's a pressure, constant pressure, which is NCBM delta T. And the work is going to equal negative B delta V. So really, there is nothing here. None of the condition, none of the thermodynamic function will equal to 0. So when you're working at constant pressure, none of the thermodynamic functions will equal 0 because as you can see, they all basically don't have delta B as a relationship with them. The work is a B, not delta B. So this is negative B delta V. And this B is a constant pressure that you already work at. The change in volume will be given and you're able to determine the work. The same thing for delta H, delta U. The last final experimental variable that a given ideal gas can be under is adiabatic condition. Adiabatic condition means there is no heat loss or gain to the system, which means Q is equal 0. So if Q is equal 0, then there is no heat provided. So Q, this is 0. And if this is 0, then delta U equal W. And what is delta U again? NCVM delta T. And what is delta H again? NCBM delta T. As you can see, how many times this equations has repeated itself. What you're looking at right now is the different models to determine the thermodynamic functions of a given system at these different experimental variables. How can you determine CBM from CVM? Here is the equation that relates CBM to CVM. So CBM will equal CVM plus R. So if you are provided with CVM, all what you need to do is add R. And remember, R is the universal gas constant. We are dealing with an ideal gas. So this R here is the universal gas constant. So here is the first model. Constant temperature, which is isothermal condition. I mean, IE delta T equals 0. You're going to use the first law of thermodynamic. Delta U is going to equal NCVM delta T. Since delta T is 0, then delta U will equal 0. And Q will equal negative W. What is W for reversible isothermal? Here is the relationship of W for reversible isothermal. Negative nRT ln V2 over V1. From the gas law, you know that Boyle's law, B1 V1 equal B2 V2. So if you're not giving the volume, but giving the pressure, how can you calculate the work? You're going to use nRT ln B2 over B1. So all I did, I expanded on this by putting down what exactly the work. What is the model for the work when you are working under isothermal condition? By abstracting the information from here. So E here, which says isothermal reversible expansion. I abstracted that model here for the work and is, again, as I said here, in this general, again, idea. So every single time you are working under isothermal condition, these are the type of calculations you're going to be performing. And depending on the experimental conditions, the volume or the pressure, you're either going to use the volume if it's giving you V2 and V1, or you're going to use the pressure if it's giving you B2 and B1. And look at the two difference. The negative is gone. Why the negative is gone? Because they're opposite to each other. From Boyle's law, B1 V1 equal B2 V2. It's an inverse relationship. So if you want to keep B2 over B1, you're going to have to reverse the sign, and this become positive. All right? So this is, again, for the work. And remember, what is Q? Q is negative W. So once you get W, you can get Q. So right now, in this model, we determine delta U equals 0. We determine delta H equals 0. We determine Q equal negative W from the first law of thermodynamics. We know that the work under reversible isothermal condition is negative nRT ln V2 over V1. I show you where that model came from, which also equal nRT ln B2 over B1. depending on which condition is given. Are the problem giving us the volume or the problem giving us the pressure? All right, so constant volume, which is again the second condition that went over. The constant volume, which is isochore condition. That means delta V is equal 0. If delta V is equal 0, then the work is 0. As you can see from this here, the work is 0. And that means delta U equal Q. And what is delta U equal to? NCVM delta T. So once you get the delta U, you can get Q. And what is delta H? NCVM delta T. So what you need here, the change in temperature, the CVM and the CBM. And I show you how to get the CBM or the CVM because one of them will be given, not both of them. The question will only give you one, and you will use the relationship between them to get the other. So this is constant volume. Constant pressure, where delta B equals 0. Again, you will able to get the work, negative B external delta V. This will not equal 0 here because you know the pressure and you know the volume. Delta H will equal Q. And delta U will equal NCVM delta T. Delta H will equal NCBM delta T. So again, all of these, as I said, there is no non-zero function here. So all the functions, all the thermodynamic functions will not equal, none of them will equal 0. Then the last experimental condition, which is the adiabatic conditions. And this is again Q equals 0. So delta U equal Q plus W. And again, Q will equal 0. Delta U will equal W from this law here, first law of thermodynamics. And we know what delta U equal to and what delta H is equal to. All right, so this pretty much is the calculation in the fundamental of thermodynamics. And this is basically the basis for what we're going to build on. You will see me talking about these models as we cover, again, thermochemistry, as we cover entropy, as we cover free energy. So as we introduce more thermodynamic topics, this is the foundation for, again, for thermodynamics. And it is very important to understand this foundation. Here is the summary of the, again, the calculations at different experimental conditions. All right, so the best way to understand these different models is to go over an example. All right, so you are giving 1.5 moles of an ideal gas for which the molar heat capacity, CVM, so you're giving the CVM, 3/2R, initially at 25 degrees Celsius and 1 atmosphere, undergoes a two-stage transformation. So that particular gas is undergoing two-stage transformation. Calculate Q, W, delta U in kilojoule for the complete process, which means summing both processes. All right, so here is process A. The gas is expanded isothermally and reversibly, isothermally, until the volume doubles. Condition B, beginning at the end of the first stage, the temperature is raised to 100 degrees Celsius at constant volume. So these are two experimental conditions that was carried for that gas. The first experimental condition was isothermal. The second experimental condition was isochore, it says constant volume. So the first condition, we know already that if it's isothermal, delta U is 0. So automatically, isothermal condition, delta U is 0. And Q equal negative W from the first law of thermodynamics. So this is our first. So for A, delta U is equal 0, Q equal negative W. So delta U is 0, Q equal negative W. How we calculate W for isothermal reversible? Negative N RT ln V2/V1. Do we have information about the volume? It says until the volume doubles. The thermodynamic models or the thermodynamic calculations or problems is going to be a multiple lines problems, but you have everything pretty much given. You just have to abstract the data as you're reading the problem. So it says the gas is expanded isothermally and reversibly until the volume doubles. So that means this will be ln 2, because V2 over V1 equal 2, right? That's double. So what is N? 1.5 moles. What is R? 8.314 joule per mole Kelvin. And again, from here, you will get your energy, and you divide by 1,000, and that will, again, will be the work in kilojoule, minus 2.57. Now, what is Q? Q is negative W. So Q will equal 2.57 kilojoule. So the work is negative 2.57 kilojoule, and Q is 2.57 kilojoule. How we get that? From the relationship between the Q and W. And how we get the relationship between Q and W? From the first law of thermodynamics. Delta U is 0, Q equal negative W. So this is delta U and Q and W in the first condition. Now the second condition is constant volume. You're working under constant volume, which is isochore conditions. If delta V is 0, then the work is equal negative B delta V, which is delta V goes to 0, and this will equal 0. If this equals 0, then delta U equal Q from the first law of thermodynamics. And what is delta U equal to? NCVM delta T. Do we have N? Yes, 1.5 moles. Do we have CVM? Yes, 3 over 2 R. And what is the value of R? 8.314 joule per mole Kelvin. Do we have the change in temperature? It says the final temperature 100 degrees, the initial temperature is 25 degrees. So 100 minus 25 Celsius. You don't have to convert here because you're subtracting. Multiplying everything, it's about 1400 joule, which is about 1.4 kilojoule. So 1.4 kilojoule, this is delta U and also Q, because remember they equal each other. So now all we need to do is add the respective thermodynamic functions in A and B by adding their values, and that will give you your answer here.